Now we're going to go over centripetal acceleration. We've already defined this in class as the centripetal acceleration. The magnitude of centripetal acceleration is equal to v squared over r. And this v really is speed, because when we're talking about centripetal acceleration, we're talking about an object moving in a circle. So this might be the radius, r, and when this is moving, the velocity is always perpendicular to the radius. And so this velocity is constantly changing, so we're not actually talking about velocity, we're actually talking about speed here. And when we're talking about acceleration here, we're going to prove that the acceleration is towards the center of the circle, but what we're talking about is the magnitude or the scalar component of the acceleration. So let's just do a quick review. We remember that this might have a certain speed, which we might call omega, which is our change in theta over our change in time. But as we remember that the velocity changes, and that velocity is going to be, or the speed is going to be dependent on the radius. Let me rephrase that. So the velocity of any point along this radius is going to be dependent on how far away it is from the center of the circle, or r. So we'll have these as all, this might be an r1, and this out to this is r2, and this might be r3, and so on and so forth. So it's going to be dependent on that value of r. So if we actually were to solve this, then it ends up being that the velocity is equal to omega r. That is to say, as the velocity goes up, the r goes up. As the r goes up, the velocity goes up. So if I were to just create a quick graph of this, and I held my omega constant, then I end up with a constant slope. So it's directly proportional, and this actually ends up being the slope of the velocity versus, that's not omega, r. The slope is equal to omega itself. So this is what we're working towards right here. But first we want to prove graphically the direction of the acceleration itself. We talked on the other day about what is the direction of the acceleration. We talked about the direction of the acceleration being towards the center of the circle. Here's a circle, kind of. And I end up, I'll just draw these as 2 points. I'm going to try to represent that this has an omega, and it's moving from, let's say, this initial position right here to this final position right here. So it's rotated a certain theta. And so here is our v final, and this would be our v initial. And if we allowed theta to get smaller and smaller and smaller, this arc length essentially equals this distance right here. I know it doesn't look that way right now, but if I allow theta to become very, very small, the arc length essentially matches this straight line between. So those are going to become the same value or approach the same value. Right, so let's kind of file that away. So let's think back to what acceleration is. Acceleration is the change in velocity over the change in time. And the change in velocity is going to define the direction of the acceleration. Okay, so if we're looking at changes in velocity, then we should be looking at, let's see, change in velocity is v final minus v initial. Okay, so my v final is something that looks like this, and a slightly downward slope, so I'm trying to bring this directly over here. And my v initial minus v initial, so my v initial would be this way, but it's a minus v initial So it would actually be going in the other direction, minus v initial. This is my v final. And so then my change in velocity ends up being right here. And the direction of the change in velocity is going to be in the same direction as the acceleration, my centripetal acceleration. So if I actually then transfer this velocity over to my circle, that velocity ends up being in this direction, or my acceleration ends up being in that direction, towards the center. And that's what centripetal means. Center, petal is seeking, so it's center seeking. Acceleration is center seeking. All right, so now let's see here. I can define this as r, this is also r. And if we're going to try to solve for this equation up here, let's do that by looking at these similar triangles. So I know that this is perpendicular,